easy, I think, for most people. So what I asked for was just basically to solve the Friedmann equation and find the scale factor as a function of time. And that normally, this is all generically solvable. And I will actually do it, I will solve num D first, just to be a bit contrary. So in D, or maybe I'll use black, it's more visible. So D very simply asks to define the pressure. Let me actually get the right one up. Set that to be some W and then rho C squared. So you say that the pressure is something that is proportional to the rest mass energy of the gas. And this is is convenient because for different W's you get different types of matter. So if I put that in, that means that rho plus P over C squared, this term here, of course, is only 1 plus W times rho. Okay, so that's nicely simplifies this. And you put that in here. And what you have is you have d rho dt equal to minus 3, 1 plus W. And here you have dA dt over A. And so, since I'm not giving a math lecture, I can just multiply by dt on both sides and a rho, there's a rho here, and divide by rho. So then I get d rho over rho equal to minus 3, 1 plus W dA over A. So if that sort of insults your mathematical inclination, you can always do this in a, not in infinitesimal units, but in just finite little blobs, so delta rho over delta t, and then you can see it all works. You can do it right as well if you want. And so what this gives you when you integrate it up is ln rho is minus 3, 1 plus W ln A plus a constant. Okay? So that's just integrating 1 over x. And you get rho is proportional to A to the minus 3, 1 plus W. And so that conveniently gives you the solution here, but it also lets you say how rho will evolve in different conditions. So for W equal to 0, which is matter, you get rho proportional to A to the minus 3. That's matter. And W equal to 1/3, which is radiation, you get rho proportional to A to the minus 4. And the final one is the cosmological constant when W is minus 1 and then rho is constant. And you can put in any W you want, and it gives you some evolution between constant and A to the minus 3 typically, if it's a negative value. So the usefulness is that this is the first equation you need to solve. I didn't really expect you to solve it because I had given the result in the lecture, but it's needed to solve A, B, and C. Okay? You could take it from the lecture and say, oh, rho in the matter-dominated universe, rho goes as A to the minus 3, and just plug that in. And that will be perfectly fine. Okay, so now just let's solve the Friedmann equation. So let me just do it generically. So now we're going to use this one, Friedman equation 1. So I solved equation 2. That tells me how rho evolves, and that's usually you solve that once and then you don't worry about it again. And so now we're going to go to this one. And I'm just going to write A dot over A square. And I'm going to ignore the cosmological constant for now. And then it's going to be 8 pi rho over 3 for any, when something dominates. Okay? There might be many things that this might be a sum, but now I'm going to consider just one component at a time. And this, I will write, is equal to, there's a g here too, 8 pi g over 3 rho c times a to the minus some constant. And here I've set k equal to 0 because in the problem I say all the time that it's a flat universe. A flat universe means k equals 0. Okay? So this c will be c equal 3 for problem A, c equal 4 for problem B, and c equal 0 for problem C. Yeah? So it's generically, that's you don't need to do each problem over and over again. Okay. So you just do the same trick that you did here. So you get dA over dt is equal to, just multiply things over. So it's going to be 8 pi g 3 rho c to 1/2 and a 1 minus c divided by 2. Okay, that's just moving this one over on this side and taking square roots. Now this we can simplify because it's a flat universe. The density must then be the critical density. So I can put that in here. This is actually h naught. Okay, I should have a 0 here indicating that is today. So I take today and I evolve backwards. So this is h naught from this relationship. So that's convenient. It means that dA, dt, I'm just going to write it explicitly, is h naught a to 1 over c over 2. And then you can integrate this. Now this can be integrated over quite easily. You divide over on the other side. You have dA a to 1 minus c over 2. And that's h naught dt. So if c is not equal to 0, okay, if c is equal to 0, this becomes the natural logarithm. So it's the same solution as here. But let's just assume it's not 0. Then you can do this integral very easily. It's elementary. And you get 2 over c a to c½ is h naught t plus constant. Okay. So that's just generically just integrating it up. This constant is going to be 0, okay, because a of 0 is at start, the universe is supposed to be a point 0 size, so it has to be 0 when time is 0. And then that gives you that a is c h naught 2 times the time to 2 divided by c. And now you can put in c of 3 or c of 4, and you get these two solutions here. If z is equal to 0, then you have to integrate dA over A equal h naught dt. And that is now a natural logarithm. So you take the integral, you do exponentials on both sides, and then you get that A is proportional to E h naught times t. So you see that when the universe is dominated by cosmological constant, it expands exponentially fast, which is infinitely faster in some way than the other cases where it increases as a polynomial. So this really blows the universe apart. That's why it's a little bit annoying. So that's the basic way of solving problem 1, and that should be relatively easy. I don't think there is anything in there that's not elementary. Yeah. Yeah.
Who did it? No? So that's the question.
Yeah. Now the second one, I think this all of you should be able to do. Okay, problem 1 here, all of you should be able to do it. I'm sure you can do it if you sat down and tried to do it. The second one is more complicated. It is also relatively easy when you've done it. But to come up with how to solve it is not always so easy. So the aim of this, the history of this problem, is that Peter Mscharosz, who calculated this solution first, he wanted to understand what happens with perturbations in the period when radiation was dominating the universe. So were they really constant, or did they change a little bit, or what happened? How did that period really behave? And so he used this perturbation equation. And so I'm doing these problems, to some extent I'm doing these problems because the sum of what I'm doing might be useful for the homework that's to be handed in, right? So I'm not going to solve the problems you have to solve, but at least some of the techniques and ideas should be in what I'm doing here. Okay, so what's the aim here? Well, firstly, I've written down the Friedmann equation, slightly different way. I've used h instead of a dot over a. And we want to reach an equation which is looks quite similar to the perturbation equation. This is the perturbation equation. But I need to change variables. And so really that's what it is. It's a change of variables. So the first thing to realize is that there is one term in this equation which has sound speed in it, Cs. Sound speed only matters if you have real pressure. So the sound speed of cold dark matter is 0. So for cold dark matter, this disappears. For baryons, it does not disappear. So if you were to solve this for baryonic matter, you have to take into account this term, and it becomes quite ugly. But we can ignore that. So what we're left with, we can ignore the gradient. So we're only left with a second order derivative with time and a first order derivative with time. So I need to change 2 variables. And they want me to use a variable which is eta in here. So let's just write this down first. So eta is the ratio of baryon density to the radiation density. Well, did I use R in there? No, I used gamma. It's the beauty of being consistent. Okay. So it's useful to now go one step further. So for that, it's best first to think about this variable. What does it mean? And So when is this variable 1?
When?
So if I write it differently, if I write it eta equal to 1, right, that means rho b equal to rho gamma. So was that something we talked about yesterday?
Yes. Was that before last scattering?
It's before last scattering. It's the time of equality. So it's the time of matter radiation equality. Okay? And so this is where it's useful. Okay? Because this on its own is a little bit, I need to understand what is d eta dt, right? That's for changing variables. I need to understand what that is. And I have it like this. Maybe it's a bit confusing, and maybe it isn't. I don't know. Depends on your preferences. But it is useful, perhaps, to think about it in terms of equality. So that means that eta, which is rho b over rho gamma, is also the same as A equality, sorry, got it upside down. A over A equality. Okay. So do you see that that's how it is? Because this depends on A. This is proportional to A to minus 4. And this is proportional to A to minus 3. And so when you combine the two, you get A, and it's normalized so that it's 1 at the time of equality. So these two are equivalent. Okay? Which one I use is the same. It's part of the trick. So thinking about what is the ratio of matter to radiation, what does that really mean? It was used in here, and the reason why you use this variable is that you want to move from a time when radiation dominates to a time when matter dominates. And so you want a variable that's sensible. It could be 0 or 1, but usually you want it to be 1, where things are balanced, so that it goes from 0 on this side through 1 to maybe to infinity in the far end. That's why you use this variable. This variable is very useful. It just has a useful scale when physics change. So that's a very common thing you do when you have a differential equation and you want to change variables, is you pick a variable and you choose it so that it has a nice value when the physics change in your system. It might be very small when the physics change because you might want to do perturbation analysis, or it might want to be 1, or it might be 0. It depends on your physics, what's the right thing to use. Here you want to use this variable because it is the one, it's the physics. It has all the physics in it. Time doesn't. There's no physics in the time here. It goes along, and time doesn't care about whether matter dominates or radiation dominates, but this one does. It sort of gives you a sign when that happens. So when you have figured this out, the rest is boring, but fairly straightforward. So let me do that, because it's useful, again, as a trick. So you do d delta d eta, which is a terrible Greek letter because it only looks like a squiggle on the screen. And so that's d delta d eta. Oh, sorry, what am I doing? This should say dt. Sorry. At least, otherwise I get my writing screwed up. And then this is times d eta dA times dA dt. And so now the next trick is you want to get A into the business, because you know what happens with this scale factor. The scale factor is very often what you want to have in your equations, because we know what the scale factor does, and we know how it fits into the Friedman equation. So eventually we want to make some use of this. Okay? So this is just the chain rule for change of variables. And this is reasonably easy. D delta, d eta. This one, you know, because it's here. D eta dA is 1 over A equality times, times A dot. Okay? And this ratio is not so useful because I don't know really what that means. So I would like to get this one in because that's eta. I know what that means. So I can do that by multiplying and dividing by A. D delta d eta is A over A equality times A dot over A. Okay. So I just multiplied and divided by A. And then the nice thing now is that this here is eta and this is H. Okay. So that's the nice and convenient way of changing variables. And that means that d delta dt is now d delta d eta times H times eta. Okay? And so that's just standard change of variables in a derivative. So if you had realized this, then I expect all of you can do this easily. I mean, it's just you have to be a bit careful to get it right, but it's a standard mathematical operation that all of you will know how to do. And I'm not going to bore you, but if you haven't done it, you can now work this out yourself. And let me see if I get the right slide. Okay, and that's eta squared H squared plus So that is a little bit longer, but it is just taking the time derivative of this expression. There's nothing more complicated to it. You know what the time derivatives of eta is, and you can work out the other ones. But definitely, if you didn't do these other things, then doing this step is a good idea. It just will take you a couple more lines, or maybe a page. Okay, so now there are a few things, and now it's where you have to go back a little bit to put some more physics in. So firstly, we need to get some expression for this here. So, and the whole trick now is, of course, to go back and use the Friedman equation. So usually what we do, simplest approach sometimes is we solve this equation, we get a result for A, and then we put that solution for A into this equation, and then we solve this equation. That's easy. Unfortunately, if you were to do that trick here, you would get a differential equation which is not easy to solve. I mean, it's easy to solve on the computer, but it isn't easy to solve analytically. So that's why this trick does the job for you. So now, what you need is you need to get this expression, but you want eta in there, okay? Because you need to connect it to all these terms here. So you need to understand what this is. So now you just write it down. This is the next step. You write h squared is 8 pi g rho matter 3 rho gamma so you see what I've done is I just take in rho matter outside, and this is of course 1 over eta. Okay, so that's now 8 pi g rho m 3, and then it's eta plus 1 over eta. So now it's a lot nicer, and you can solve this now for rho m. And the reason why you want to get this rho m for two things. Firstly, you want to understand what your derivative of h is with terms of eta, but you also need to do something with this part, the 4 pi g rho delta. So let's do that one first.
So
yeah.
This rho m includes baryonic and dark, or only dark?
Only dark. Only dark, yeah.
Yeah, because rho b is the baryonic one.
It's, yeah, sorry. It's, this unfortunately, there is very confusing notation. I didn't think about that. So normally I try to, but I usually don't remember, to use a capital B for baryonic. And B in the literature normally means background.
Background. Oh, okay.
Important thing, yes.
But this background is made by.
It's made essentially by yeah. The problem is, I clearly solved this. I changed the notation in here to be clear, but then I didn't change it when I solved the equations. So these ones should all the places be m.
Okay.
Yeah. Now it's I had the first time I made this problem set, I used B when everybody got confused by it, but I had my solution and that used B, and then I changed it to say M because M is clear.
Matter.
M is matter, yeah.
Matter, yeah.
And
Matter, but is the combination of baryonic and dark.
so what I'm doing here is actually only using dark matter.
Only dark.
Only dark.
Okay.
Because the problem is, it's possible to put, possible to put in baryonic matter here, and I could do that. The problem is then I cannot ignore this term, and so then I get, in fact, I can write that down. So what would happen if I included baryonic matter is that, let me write it here because I need a bit of space. So in that case, I would have to write delta B for baryonic plus 2A dot A delta B plus, no, it's a minus, isn't it? Minus CS squared over A squared gradient delta B equals, and now I need more space even. Equal to 4 pi G rho B, so the baryonic density, plus rho dark matter times the perturbation in the baryons. So that'll be the first term, but that's not the complete solution yet because I have a system of differential equations, and I would have to write down dark matter plus 2a dot a dark matter. And this doesn't have any pressure, so I can ignore that term. And you get 4 pi g rho b plus rho dark matter delta dark matter.
Okay.
Yeah. So this particular set of equation doesn't have anything from radiation because radiation is smooth. It has no perturbations. So now you then need to solve this equation. So A will be the same. It will always be the same for the universe, background universe evolves, and these perturbations are very small, so it doesn't affect it. So the A is the same in the two equations. And the coupling is here, so that's where they coupled. And you could then, in principle, do exactly the same analysis through this. But you're left with a gradient here. And so to deal with that one, you would have to Fourier transform these equations. So you're in Fourier space, and this one becomes a k squared, and you get Jeans analysis. And then you can solve this set of equation, but I don't think you can do it analytically. I'm pretty sure you can. But so usually what you do is you can plug in a solution. So you can say you find a solution for dark matter. You assume first that there is no baryons. You get a solution. You plug that one in here, and then you will find that this here is going to be, let's see if I can remember more or less what it is. I think it's if dark matter is much larger than dark baryons, I think the solution for the baryons is going to be something which is, and this is in Fourier space, so it's going to be k over the Jeans scale times the dark matter. It's asymptotically a solution of that form. So on very large scales, very small scales where k is very large, you have no perturbations in the baryons. And very large scales where k is 0, it's the same as the dark matter because pressure forces have no effect. So that's sort of the two scales that you get. And then this sort of interpolates between the two. But it's not quite the right solution because there is also, of course, a ringing solution because this is a Jeans solution. So you don't have only collapse. You have a sort of oscillating solution as well. But anyway, that takes us a bit too far away from this particular problem. So let me go back to this this bit. So what I wanted to get here was basically calculate what 4 pi, and I cleverly erased the equation I needed, 4 pi g rho matter delta. So I can take the solution I just had here. There are some faint residues right here. And that's 4 pi g times 3 h squared 8 pi g eta plus 1 times delta. And so that's now simply 3/2 eta plus 1 h squared delta. So that's the right-hand side of this equation. And you can now put everything in, and it looks a little bit hairy. So the full equation now is eta squared h squared d plus eta squared. I'm just writing this out again now because I erased it. Okay, so that's now the full equation after you changed variables. And the only thing that's left now is to calculate what dln or dh dt is. Dh d, sorry, eta. Oh gosh, I can't write. And that you can get from the Friedman equation, just what we did earlier. I said that in a previous one. So the simplest thing is to do dln d eta, which is 1/2 dln h squared with d eta. So this is a very common trick, okay? So that you've probably seen many times before that you can write dln f dx, that's 1/f df dx. Okay? So it's just a trick to go backwards to do that. And this we know because we had an expression for what h naught was. And this is -2 eta plus 1/2 1 plus eta. Okay, now I'm not going to do the rest. You can just put this in here. It simplifies this bit, and you get precisely this equation in here. It's not. It just reduces nicely to do that. Now, the last thing was to ask us to show that there's a simple solution for this. And that is that delta is 1 plus 3 eta 2. That's super easy. Okay, you have the equation. You just take the derivative of delta with respect to eta. The second derivative is 0. The first derivative is 3/2. You can plug that into the equation. That's very easy. But the important thing is, what does this mean? Okay, because what's the physics in this? And here it's useful to go back and write what this expression means. So put in what eta is again. And so that means that the true solution at some position in space at some time is going to be some spatial function. Remember, there's no spatial information in this differential equation, so you can't solve that. But there's some spatial function times 1 plus a equality 3/2. So what this is basically saying is how perturbations grow in the period, both when radiation dominates and when matter dominates. It actually solves for both. As you see that when this becomes 1, so when A is equal to reaches matter equilibrium, matter radiation equilibrium, it has grown from A equals 0, which is very early, to A equal equality by a factor of 5/2. Okay, so it's grown a little bit, but this is a very long period of time. The scale factor has changed a lot, but because there is a 1 here, the growth has been very, very slow up until equality. As soon as you reach equality, this becomes bigger than 1, and you're dominated by this term. And it basically starts growing linearly proportional to A. So for A much less than A equality, delta is constant, right? Because this term is very small. So this is basically constant. And when A is much larger than A equality, then delta is proportional to A. Okay. And it just basically says that as you get close to the equality time, that's when there is a bit of growth. And that makes sense, right? So when radiation really is dominating, the universe expands really quickly. There's no growth. But then as you get close to where matter becomes to be important, there is a bit of growth by a factor of, 2.5. So that's that solution. That's the Musharosh solution. And I think there are certainly tricks in here, like the change of variables is very useful in many situations. You get the most common situation isn't to use eta, but you might have an equation which is given to you in terms of derivatives with respect to time. But what you actually want is derivative with respect to scale factor or redshift. Okay? So you need to know how to do these changes. So you have these d dt, and then you might have to do dA, dt, dA, for instance, and you use that approach to get, and so that's of course a dot dda. And you can do similar tricks with derivatives with respect to redshift, etc. So that's a trick, that's a method of simplifying equations, rewriting equations, which is very useful. The other thing is to jump back and forth and get in the Friedmann equations. So you do start some solution, and you're a bit stuck, and you maybe you'll go back and you use something like the Friedmann equation to rewrite your problem to make some more sense of it. So any questions about that? Was that reasonably clear? If you hadn't tried to do this, it probably wasn't very clear, but that's your fault and not mine. If you did try to do it and you still wasn't clear, then it's my fault.
So those few problems that you solve here, they would solve for today, right?
Yes, this was solutions. This was problems for today. Yeah. So some people have looked at it, not everybody, but that's it's a busy period for everybody as well, which is making it complicated, which is why I'm doing them here in the morning, so that even if you didn't have the time to do them, at least we can go through the important steps of solving them. And this is particularly for the people that then are going to do problems and hand them to me, because they will want to have seen some of these solutions before. Okay, so now what I wanted to do was to switch gears a bit. Oh yeah, no, sorry, before I do that, I sent an email which many of you probably have not seen yet, but I changed the layout of the problems. So I now have created a file which I might be able to find. So there's a single file now on the web page which only has the problems that are to be handed in to me. Okay, so it has this one which I gave yesterday, showing that how flat the universe was. It's one about horizons, or doing horizons properly. And then today there is I think this is less work, I think, than the previous one. It's something we will cover later today about scaling laws, ways of explaining simple relations for galaxies. Then there is a difficult one, which is problem 4. This is challenging, but you can do them. I mean, there's nothing in here that's complicated that you will not have seen in the problem set before, but it's not a trivial problem. When I gave it as an exam question, people were a little bit upset with me, but most of them managed to do it. So, and finally, there's a 5th one which is a bit different, and that's basically a set of 5 short questions where you're supposed to tell me whether my statement is true or false. And if you just write true or false, you get 0 points, even if it's right. Okay? So you have to explain why it's true or why it's false. Okay? So that's the set, and that's on the web page. So I will go through then. For tomorrow there is another small problem to work on, which I go through in the morning. And I will also go through a problem of this kind with you on Friday morning to sort of give you a feeling for how these are solved. Many of them are similar. Okay, so let me go back actually to yesterday, because there was one thing I didn't solve properly. And I said chances were if I did this, without notes, I would probably do it wrong. And this is quite useful, particularly for the more difficult problem in the problem set, where you have to use a similar thinking. So let me go through this. Really need to explain to you how this works. Okay. So the story was that depending on when these perturbations enter the horizon, so how big they are, you got these different ways of evolving the parameters. So let me start with this one. No, actually, let me start with this one. This is easy. Okay? So let me see, how does a perturbation of that kind work? So this is R greater than R equality. And now I'm going to start at some early time, and I will, by some magical mean, have an initial perturbation. So at t equal t initial, I have the delta is delta I. Okay? So this might be given to you by somebody in theoretical physics, or it might be something that you take out of a hat, but it's not something that we need to solve here. Okay? Somebody will give it to us. So let me see, okay, well, I now want to evolve it up to A equality, because that's where the slope changes. And that's quite easy, because I know that in that case, the first step, so this delta is going to be delta I times A over A equality squared. Okay? It's just going to go as A squared. I'm just normalized it by A equality here. No, sorry, what am I doing? Sorry, it's completely rubbish what I said there. So before A equality, it goes like this, okay? There's some scale factor where you start. That's where your delta initial was. And then it scales as A squared until A equality. Okay, that's when it changes slope here. So that's how it evolves until then, and then it continues evolving. So then we can do that. In that case, this is delta I, A equality, AI, because I really care about what's happening today. So I'll go through this point. So I've done all of this until here. And now I have to change the slope, and then it just scales as A over A equality. Right? So that's how that's evolving, this whole thing. So when I'm here, I can tell you what that perturbation is like. It's going to be the initial times this factor times that factor. Okay, is that clear? Because this has to be clear before I go on to the next one, because that's a little bit, it's the same thing, but it's a little bit more fiddly argument. So now I have to do the same thing, but I have to stop. I have to stop for a while. So now let me do that. R, S, R. So it's to start with, it's quite easy. I will say, okay, I I do exactly the same thing. I have first, it will evolve in that squared fashion until this A enter. Okay, I don't know what that is right now, just let's use it. Okay. So that's exactly the same as I had here. It's delta I means A enter divided by AI squared. That's just that first bit of evolution. Okay? Just this bit here. And here, I'm going to say it's completely constant. In the previous problem, we actually solved the equation, but let's ignore that. Just put it to constant. So then that's going to be a 1. Okay, it's not going to do anything. I'm just going to put it in. And after that, it's just going to stay constant until I come to A equality. So then I can say, okay, nothing is going to happen. And then after that time, it will evolve exactly in the same way. So then it's A over A equality. Okay? So that's all perfectly fine. And so what I have done here is I have thought about what the different regimes are. When is it dominated by radiation? When is it dominated by matter? When is it inside the horizon? When is it outside the horizon? Those are the things I need to keep in mind. And you always need to do that, even if it's a more complicated history in the universe. But this doesn't quite suffice, because what's A enter? And that means little. I mean, there's no physical information in A enter, or at least I don't know anything. So you need to figure out what that is. And so to do that, the simplest thing is just to write down A enter is when the size of my perturbation is equal to the horizon. So I can write that down. And so at time of enter, my perturbation, which I'm going to say has the size lambda, that's the size of my perturbation, co-moving size. So that's what I'm going to say. That's true because now the perturbation is the same size as the size of the horizon. This is how far light has been able to travel until this time in history of the universe. So that's effectively the horizon of the universe. It's very similar to what I used yesterday. I used 1c divided by h naught. But the h naught gives the age of the universe, and that's the age of the universe at the time of entry. And I can write the same thing down for equality. T equality is equal to A equality times lambda equality. So that's sometimes called the horizon at matter radiation equality. So that's how big the universe was. In a way, it's the size of the universe at the time of matter radiation equality. Okay, so I would like to make some sense of this. And to do that, we go back to the first problem set. So in the first problem set, we showed that in radiation dominated, A is proportional to T to a half, or T is proportional to A squared. That holds whenever the radiation dominates the universe. So when matter dominates the universe, there's a different exponent. Same we did in the first problem set, but here it's this domination. So you need to keep track of when radiation dominates, and that's when it evolves like that. And that means that you can now write this down, and you will get A enter over A equality squared. That's this side. the ratio of the left-hand side, is equal to A enter. Sorry, let me see which way I did it. Enter A equality lambda over lambda equality. So now I can put this into here. Because this tells me that this expression A enter over A equality is lambda over lambda equality. So if I use that in here, I'll get the delta I times A equality AI squared A over A equality is lambda over lambda equality squared. And this now is precisely, I hope, the expression here, except I used R instead of lambda. Okay, so you see this is exactly the same thing, and I ignored the 0 here, but otherwise it's the same. And now the important thing about this is that a size is of course directly related to a mass. Okay? Mass is size to the 3rd power. So the size is mass to 1/3 power. You could put in a mass here instead of lambda. And it will tell you how big the perturbations are for objects of a given mass or a given, size. And this lambda equality we can calculate. That's just set by the time of, you need to calculate the time of matter radiation equality. That's always a necessary piece of information. And when you know that, you can calculate what's the size of the horizon of the universe. And this is the characteristic scale that you can see in the sky. Okay. So if this was confusing, and you're going to do the problem sets, I strongly recommend that you go through this and understand it. Because if you don't understand this, you have no chance on problem 4. Okay, just being that blunt. But it's not very difficult to do this, but it's this step here is usually where most people get confused. Okay? This step here, understand what that is. If you don't understand, come and ask me to explain it again. Okay? But this is a crucial step and very easy to get confused by. Every time I do this without notes, this is where I make a mistake. Typically because I get them up, my ratios upside down, but it's very easy to get this wrong. And so if you get this, if you understand this, and you're organized, have an organized mind, then you can do problem set 4, no problem. But you need to understand this 2 lines. Okay, I'm going to give you a break from that particular bit for about 5 minutes, but let's move on to the next level. So what we did yesterday, I actually find a little bit boring, because there's not that much relation to things that we can see in the universe. Oops. So what we did there was everything was completely linear theory, and if we could only use that, it's almost irrelevant because it only considers things that are so small, so perturbations that are so small in the universe that they have nothing to do with galaxies. What we're going to do today is we're going to develop something called spherical collapse theory, which is a clever way of cheating. And we're going to use that to calculate mass functions of galaxies. And you'll see that's quite heating. So here, the motivation then is we want to understand why galaxies are not equally likely to have any given mass. I mean, why is the number of galaxies as a function of mass not a constant, for instance? Why does it vary with mass? Related to that, but it may be not obviously at the moment related, is the fact that when you observe galaxies, they're distributed in space. But the question here, are they distributed in a random way? Or if they're not distributed in a random way, is there something we can learn about them by the way they're distributed in the sky? And I'm going to start with this bit. And I'm going to start very, very slowly. And we're going to look at likelihoods. So have you all had probability theory? Like chance calculations? No? So let me, I'm not going to use very much of it, so I'm going to do it very slowly. Now, okay, imagine I have a bunch of points here. And I put down a small box. Or maybe I can put it down here, or I can put it down here. Anywhere, I can put down randomly a little box, which is the same size here. And then I can ask now, what's the chance that inside my box there is one dot? Okay? So in the language of probability, that is written, if I'm being explicit, in box something. Okay, so what will I do? Well, it will depend on the size of the box, right? So that's kind of obvious. So it has to depend on area in this case. It must depend on area or volume if I'm doing it in space. Okay, so that's obviously has to depend on that. And it has to depend on that linearly. It doesn't depend on the area squared, right? I put something here and I make the box, the area twice as large, I have twice as much chance to have a dot inside. So it must depend on the area. The other thing it must depend on is how many dots there are per area. So if I define n bar to be the number, total number, over total area or volume, okay? That's the mean density, okay? And so the chance of finding one dot in here is then basically going to be P dot in box. It's going to be the area. I'll call it dA, or no, sorry, I'll call it delta A. Delta A times the mean density. Okay, that's what probability. Probability theory is not more complicated than that for this kind of level. And so that's just a chance. So I can now generalize this. I can use exactly the same argument, and in 3 dimensions, in 3D, it's going to be delta volume times the density. Okay, that's exactly the same thing. I'm just using a 3-dimensional object instead of a 1-dimensional. Okay, so that's fine, but that's kind of useless. I don't really care about it. There's no information in here. But now I want to do something else. I want to, again, do the same dots. And I'm going to have one box here. And I'm going to have another box. So that's one. Oops, maybe I should use the same color, be a bit clearer. One. And two. Okay. So what I now want to do, and this is a lot more interesting, what I want to understand is if I have a galaxy here, what's the chance that I have another galaxy somewhere else? Okay? Sounds a bit silly, but it actually is relevant because you can think, if things are completely randomly distributed, and I have a galaxy here, and I have another one there, the other galaxy won't care that I have a galaxy here. But if you think about it, that doesn't sound physically very meaningful, because if you have gravitation, okay, if I'm a star, and you ask me, what's the chance that there is a planet within 100 astronomical unit of my star? That's probably going to be much higher than if I asked, what's the probability that there is a planet a light year away? Because the universe is empty, right? And that's because gravitation will help things to cluster, right? When we saw these movies yesterday, the structure clumps together. Gravitation pulls things together. So it doesn't sound likely that if I have a galaxy here and I look somewhere nearby, I should have a higher chance of finding a galaxy there because gravitation will have pulled matter together. So I want to understand what this is. Okay? And so I'm going to call that now in a slightly different way, P1, 2, which is the probability of something at vector x1 and vector x2. So here, its position here is going to be x2 vector, and this one is going to be x1 vector. Okay. The vectors don't really matter, it's just a position. Now there is in probability theory, we write, and that's probably the only thing I really need to say. If x and y are independent, then P of x, y is P of x times P of y. Okay? That means that's independence. They don't have anything to do with each other. And you can see that from the equation, x, the value of x can be anything and doesn't care about what the value of y is. So this is the definition of independence in likelihood theory. Doesn't really matter any more than that. But in this case, if I say they are independent, okay, so in that case, I would have my P1, 2 will be P1, P2, and P1 we calculated here. It's delta V times the mean density times delta V times the mean density. Okay. And this is called a Poisson distribution. This is a definition of a random distribution of points. Okay. So that's sort of as randomly as you can imagine it's being distributed. Okay, so but I said that this is not what the universe looks like. What the universe looks like is more complicated than this. And for that, we can go, lost my remote control as usual. Oh, it's in my back pocket as usual. And for that, we need to be more careful about it. And so I have it written on the screen in one way, but we can do it here as well. And here the definition of x1, oh, sorry, called it P1 too. Is going to be some mean of the density in one position, rho of x1, rho of x2 times delta v and delta v2. Now this average is what I calculated earlier. I used that average earlier to get me this mean density. Okay? So you see if it's independent, the brackets here, I will write out what those brackets mean really in a later slide. This is an average. If it's independent, this would be mean rho x1 times mean rho x2. If independent. Okay? And then the mean density is this n prime. Okay? So then we're back to the same way. But this is also correct when the two depend on each other. And so how do they depend on each other? Well, to do that, we write the density as 1 plus delta x times the background density. Don't know what that background is here now, so I'm not going to specify it. Okay. So now that is the background. This is the definition of delta. I just changed the order, right? Remember delta is rho minus rho back, oops, it's badly written. Minus rho background over rho background. Okay? So if you solve that one for rho, you get this expression. Okay? So that's the same. This then gives rho 1 plus delta rho background. Okay, so now we solve that. We can now multiply those together, and that's what I've done here. And what you were left with is a convenient expression. So let me multiply it out here. So I'm going to have 1 plus delta x1, the rho background, 1 plus delta x2, rho background. That's this term in here, of course, this one in here. I multiply that out, I get 1 plus, no, sorry, not 1, rho b squared plus, and then I get this cross between the deltas here. The 1 delta 2 rho b squared. And what did I forget here? Delta 1 rho b plus delta 2 rho b. And now I need to take averages over this. Okay? So the average of rho b squared is going to be what I called the density squared. The average of delta 1 is, so do you see what the average of delta is? What's the average value of this function if you average over whole space? So the average value of rho here is it's the background density. right? And these ones are constant. So when you average over all of space, this is 0. So what this measure is just scattered deviation from 0. Okay, the average of delta is always 0. And so then you're left with, in the end, n squared, 1 plus, and then this one, which I don't know what to do with. Because these two terms disappear, and you're only left with this term. And that's what this equation is here. It's this written out here. And what it's saying is that the probability of having one galaxy at position 1 and the one at position 2 is going to be this expression plus this term. Okay? So you see, if this term is 0, then you're back to this uncorrelated independent case. Okay? So this one then measures how correlated these values are. So when this is positive, it means that there is higher chance than random to have one galaxy here and another one here. If it's negative, it means that if you have a galaxy here, you're less likely than random to have a galaxy here when it's negative. Okay? So it's like having people that smell good and smell bad. When this is positive, it's when people smell good, you're likely to have other people around them. If they smell bad, well, if it's negative, people are likely not to be close to them. Okay? That's what the correlation function measures. So this basically then just tells you how likely there is to have galaxies nearby another galaxy. And so this is what that actually average looks like when you write it out. It's an integral of these functions over all of space twice. In reality, you don't really carry out that integration, but that's what it actually defines. Right. Okay. So now we're going to introduce something else which you might or might not have heard of, namely what's called the power spectrum. And I'm not going to go through details of it very much. It's defined in this way. You might just take this, my word for it. This is a Fourier transform. And it is the Fourier transform of this function that correlates things. And it actually turns out that it's also the same as the amount of power in these perturbations. So what does that mean? So we don't need to know all the things there are about power spectra, but it's useful to know some things. So let me first say what's in here. So what you get when you put these things into different Fourier modes is that you look at perturbations on different scales. So you have, when k large, means that lambda, which is proportional to 1 over k, is small. So the physical scale is small when k is large, and vice versa, k small means that lambda is large. Okay? Large scales. Okay. So your delta k is going to be perturbations on large scale for k small, and on small scale for k large. Okay? So that's what this is going to tell you. And what this power spectrum does is it basically, by taking the square of this, it tells you how much perturbations there are on big scales relative to small scales. So it tells you how much power. So it's called the power spectrum because that's what it's usually used for in electrical engineering. But it tells you how important are the perturbations on large scale compared to small scale. So when this is 0, there's no perturbations on that scale. So if you plotted delta as a function of position, so a one-dimensional case, if it looked like this, then there are no large-scale perturbations in this. They're all very small, like they only go up and down very quickly. If instead delta x, if instead it looked like this, you see now you have a perturbation on the large scale. Okay? So this thing here would have P of k, small scale, large k. So you will have a power spectrum that basically might look like this, okay, depending on how I drew. Whereas here, the power spectrum will have a contribution on large scales and on small scales. Okay? Right? Because I have wiggles on small scales, but I also have wiggles on big scales, and that's where these two peaks are going to be. So that's what the power spectrum tells you. It tells you whether there are small wiggly bits everywhere. That's when there's a lot of power on this side of the plot, or whether it is big scale wiggles, and then there is also quite a lot of power on this side. So I'll show you an example of that later. Now, if the density field is Gaussian, and I'll write down what that really means later, then the power spectrum has all the information you need. That's what and so we've used this a lot. This is basically how we give the starting position of a universe. We give a power spectrum and we say this is what the universe starts like. And then we evolve that solution afterwards. So here are some examples of power spectra. It's a power spectrum that declines the old power laws. One that declines as the 5th power, one that declines as the 2.5, and one that declines as 1 over k. Okay? And now I'm going to show you 3 universes that I've used this power spectrum to create universes. Now you're going to tell me which one belongs to which. Okay? So this is the 3 universes. Okay, so who thinks that which one will this belong to? -1, -2.5, or -5? Yeah? So why? Yeah. On both scales. Yeah, exactly. That's the right answer. You see perturbations both on large and big scales. Yeah. Yeah. Okay. Now this one. Mm-hmm. Yeah.
Small scale.
Yeah, no, it's the answer is completely correct. I was just waiting to hear if somebody would argue against it. So here there's a lot of wiggles on very small scales, which means that this one have to have a lot of power on this end, okay, at large k values. So the blue one has the most power on this end, so this has the most small scale wiggly bits. And then, of course, I'm not going to ask you about the last one because now you figured it out. This has only large-scale structure. And so this one will have to have a lot of power for small k values. Okay? And this is basically what you will tell. So this is actually what power spectra for the cold dark matter universe look a bit like this. And this is exactly what the starting conditions of the universe look like. You put this in, and you get something like this. And that's how you evolve the universe. And they look, I did this in 2 dimensions. Of course, when we do the universe, we do 3. But that's just because it doesn't make any difference for you looking at it, and it takes a lot longer. So in practice, the way we do this is we do this in Fourier space, and then we convolve back to real space. But the technicalities of it is not very interesting. But so that's the important thing about the power spectrum. It tells you what kind of structure there is. So if your power spectrum goes up, goes down, it can tell you, do you have this kind of structure in the universe? Do you have this kind of structure in the universe? Do you have a mixture? Etc. And so minus 2.5, which you rightly said had both scales on both large and small scales, is very close to what the galaxy power spectrum looks like today. Yep?
Now, which one is more close, more like the real?
So this one is probably the closer. It's just in the middle. There are various reasons why it cannot be very negative, and that has to do with galactic clustering. So if it's only gravitation, it cannot be smaller than minus 4, but it's actually very difficult to make it smaller than minus 3. And this kind of scenario is possible to realize, but then you have to have this free streaming that I had talked about. So you basically erase all the structure on small scales. Okay. And then you can get the power spectrum that looks steeper. But that's actually what I'll get back to later. But minus 2.5 is close to what the power spectrum on galaxy scales is today. It's probably more like minus 2.3 or something, but it's close to this. And so it's an interesting structure precisely because it contains both large and small scales. You have things that forming on all kinds of scales. So we can do that now with exactly this equation that I had earlier. Okay? So let me just write it down. I'm not just showing you this because it's really quite informative. So if I want to change my growth function, which I'd written earlier as being 0 at lambda less than lambda free streaming. So if in this free streaming, it will erase all structure. And then it has this function here, which I'll ignore everything except lambda, lambda equality squared A over A equality and A equality. Sorry, wrong way around. So now I want to get this and tell me, what does this tell me about the power spectrum, so the structure of the universe. Okay? And for that, I can use a very simple situation that the power spectrum goes as the density perturbation squared. So the power spectrum now will go proportional to lambda over lambda equality to the 4th power, 0, and a constant. Because I only care about sizes right now. Okay? And don't care about time. And wavelength is proportional to 1 over the Fourier scale. Okay? So that means that my power spectrum k is going to be proportional to k to minus 4, 0, or 1 times the initial power spectrum. I ignored that one here, but it has to come in as well, because I need to ask somebody in the physics department to tell me what the initial conditions are. And they will tell you, we don't really know, but we are pretty certain that it's going to be a power law of this form. Okay? So, and that's why my previous drawing, I used power laws. They're easy to deal with. And so I'm going to use P of k at the initial time is going to be a k to some n power. And then I insert that in, and then I get this equation which you see here. Okay? So I'm scaling with a, which is incorrect. No, it's correct, of course. Yeah. So that's the time scaling. And then it has a scaling depending on the size, which goes as n minus 4 or n. So now let's draw that, because that's what's informative. Let's draw what that looked like. P of k and k. Let me start out by drawing the initial power spectrum. And it's very popular to use n equal 1. Okay? And I draw the power spectrum, the pk initial goes as e to k. So what that one looks like is then a straight line with unit slope initial. And so what happens then with the universe? This stopping during radiation dominated area is going to modify that from my k of n to an n minus 4. And this happens on physical scales that are small, so on k that are large. So on the large k scale side, I have to go from k of n to k of minus 3. So what I will get now as my final power spectrum is the same thing here, but here, which I would be k equality, which is 1 over lambda equality, I will get a turnover. And I will get a power spectrum that drops proportional to k to the minus 3. So now you can see what happens here. Okay? I started out with a power spectrum that had lots and lots and lots of power on very, very small scales. Lots of stuff. But because of this stopping during radiation dominated area, these perturbations can't grow there. They're just kept on hold. They get weakened. They drop down. And your power spectrum looks like this. And this, now, you see there is a scale here. That scale is set by the size of the horizon at the time when matter and radiation were equal. Okay? So that's what the size here is. And now remember, this is related to the correlation function. If you remember this equation here. So if I know what that function is, I can go back and calculate what that correlation function is. And that tells me when this is big, this is essentially big as well. So it means that this scale in the universe, there is a bigger chance to find another galaxy close to it. Okay? It's a characteristic scale of the distribution of galaxies in the universe. And it basically set with when matter and radiation were equal back in early universe. So it really is an echo of the early universe in the sky. And so you can use this to then constrain properties of the universe. It's not really what we do anymore, but sort of early on, that's how people did it. And you can plug this function into your computer, and you will find that at some point, or at least on relatively small scales, it will behave like that. On very large scales, it will have a very different behavior. But it will be a mixture of these various ones. It will not be a single power law anymore. But on the scales where galaxies live, this is actually quite close to this k of -3 approximate relation. Galaxies live somewhere here. Okay. Very large scales, they will be different. Then you will have a closer something that's slightly different from this. That's what it's going to look like. Okay. So this is the observations, just to show you what the real universe looked like. It's a relatively old paper, but this is not a plot that people make very much of anymore, because we're using different techniques these days, more or less. But it tells you as a function of k, what's the power spectrum in these different types of objects. You can see here they are, some of them in black are galaxies. These are Lyman alpha forests. These are tiny little gas clumps in the distant universe. Here are clusters, weak lensing. This is from the surface of last scattering, which probes really large scales, so beyond this turnover point. And now you can read off from this plot what was the horizon size at time of equality. And it's here. Okay, you can read it off. It's 400 h to -1 megaparsec. And since you know the temperature of the radiation in space, you know what the radiation density was, you can then take this and you can calculate what the matter density of the universe is. Turns out when you do that, you go wrong by a factor of 2 or so, but in principle it works. It's difficult to read off and do a correct thing. And of course here I have a sharp turnover, and there is a smooth turnover. So it's not, the real universe is of course not quite right. This slope is also not -3, it's not quite like that. But that is because there are some modifications to this power spectrum, the initial power spectrum. But at least we've explained that more or less. I mean, we've given a good explanation for why this is happening. And it's just to do with the fact that all these objects here enter the horizon in the radiation-dominated era. And that's why their power is less. Okay, that's a slightly different way of doing it. Now converting back to density, you can do that as well. Let me skip that. Okay, so this is a recap of what I said. It's a reference page. Some of it. So this is actually how we write things when we expand our density distribution in Fourier space. We write it as an integral over these Fourier modes with some Fourier components in here. So if you've seen Fourier transformations before, this is familiar. If you haven't seen it before, this is probably confusing, but you should just ignore those confusions because you don't really need to know much about Fourier space to understand what's going on. The power spectrum we now discussed. We showed how it fits up with observations. This is often actually rewritten in this form. Very often you will see in the literature, people will talk about the power spectrum, and they have a tendency to talk about the power spectrum and not say which definition they use. So there's a difference because there's a k cube in there. So that's just for reference. Now let's move on because there is one problem I've talked about. I talked about density, and I put density down in one point. And that you should all sort of throw something at me because that makes no sense. I mean, I have a, how can I talk about density at the point, right? Density is mass divided by volume. A point has 0 volume and 0 mass, so it's an ill-defined quantity. You should never ever talk about density in a point. It's a meaningless thing to talk about. And so to do that, what we do is we take the density field and we average it over some little bit of volume. Okay? And that volume, the obvious thing to do is to use a sharp box. You just make a box and you say, okay, it's everything inside this box with a sharp edge. But when you do a Fourier transform of something with a sharp edge, you get a lot of sinusoidal functions that mess things up. So generally we allow for different types of window functions. And I summarized them here. You don't actually need to know what they look like. I think the most pleasant one is one that's a Gaussian. So it's a function which, well, I should write down what a Gaussian is because we're going to use it a lot now. So a Gaussian function is in one dimension. In one dimension, it's given as, depends on the mean and some spread. It's 1 over square root 2 pi sigma e to the minus x minus the mean square 2 sigma square. Okay, that's a Gaussian function, always. And so that's the nicest one. I use this red line is a Gaussian. It converges very quickly. It goes to 0 in the outsides. And the Fourier transform of a Gaussian function is a Gaussian function, so it's also very easy to work with. Okay. But you need something that defines a volume. That's all you need to think about. Now, there's one thing. So I talked about these different scales. And there's one thing that's very nice about linear theory. So now I've taken this perturbation equation we had earlier, and I've taken the Fourier transform of that equation. And what comes out is that each k here is independent. So things on large scales evolve independently of things on small scales. So there are no k minus 1. There's no cross term. Nothing on different scales doesn't talk to each other. So in linear theory, scales on different sizes evolve completely independently. And that sounds a bit strange. You say, oh, on big scales and slightly smaller scales, why do they evolve independently? I mean, gravitation shouldn't really care about that. But that's just because we're working in linear theory. And so these effects that correlate different scales, that gravitation does do that, of course, they are second order effects. So they go away from the equation. That's why they're not here. If you write down the Euler equations, and instead of doing the analysis we did yesterday to first order in delta, but you carry it to second order in delta, then you will see there are terms on different scales. But we don't have to care about that, so they all develop independently. And so gravitational interactions on different scales cancel out. And what we think happens from various types of physics is that early on, the likelihoods, the probability of a given perturbation was given as a Gaussian function of this form. Okay? And so that means that you aren't very likely to find perturbations that are very large. You're most likely to find perturbations that are quite small. Okay? So it means if you draw this function, you will basically see that it's centered on 0. And it has a peak, and it drops off again, and the width here is given as sigma. So that's what's the chances of having a particular overdensity. Okay, so it's a chance if I smooth the, so I've taken the whole field, I've smoothed it out a bit, blurred it out a bit, and the chances that I will find an overdensity that's, say, something is going to be given by this function. Okay? I'm not going to justify this. You're going to take it as a mathematical fact because it's actually not possible to justify this properly. It's just that we'll say that the chance of having delta, this particular value, is given in this form. But in practice, what we will say is that if I write it out explicitly, and let's say the probability that delta is greater than delta c, some value, is equal to the integral 1 over square root 2 pi sigma of r. It's going to depend on this window function, okay? Because I can't talk about density in a point, so I need to use a window function, and this is going to come into this r value here. And then E is minus delta squared 2 sigma of r squared d delta, okay, from delta c to infinity. Okay, so that's what this means. Okay, this is really what it means physically. It means the chances of having a perturbation that's bigger than some particular value, or you could write it as less than some value, is given as an integral of that kind. So if you're unfamiliar with probability theory, you should ignore all I'm saying about probability. You should just take this as a defining an expression. It defines the chance of getting something. So now, in the last 2 minutes before we have a break, I just wanted to go to one last thing. Going back, and I'm going to put down lots of boxes here and calculate how much mass is within each box. Okay? So we can do that on the drawing board rather than on the screen. So I have, let's assume all my dots here have unit mass. So now I'm going to put down a box. Call that 1. In 1, I have a mass of 2. Put another box. In 2, I have a mass of 0. 3, I have a mass of 1. Okay? I can just do that. It's very easy to do. And so the two things I'm interested in doing now is I can ask, what's the mean m and the variance in m? This is defined very simply. It's the average of n boxes and then sum over all boxes. So in this particular case, I had 3 boxes and I summed up to 3. So in this case, this gives me mean of 1. Okay. In this case, to do this, well, it depends a little bit on how we do things here. Let's just write it like this. Mi minus the mean of m, which is this one, squared. Okay, that's what the variance is. And so in this particular case, this is half times 2 minus 1, so that's 1, plus 0 minus 1, that's 1 again, plus 1 minus 1, which is 0, and we get 1. And so then we would then say that the mean is 1 plus or minus 1. Yeah.
Of course, each box is the same size.
In this case, it will always be the same size, yeah. So, so in what I'm doing here, I'm going to do that. You could do it differently, but then you need to divide by the volume of the box here. So if I did it like that, and sometimes you do because you need to get enough statistics, and then you make different size boxes. So that's what these boxes are doing here. They're calculating various averages. Oops. Oh God, this is an annoying one to go through again. And you calculate, in the end, you calculate this variance of the field. It's exactly what I did here, except I divided by the mean because I wanted it to be unitless. Otherwise, if I change the units, my variance would change, and that's kind of stupid. So I would like it not to have units, so I divided by mass. And if you write out what that means, it turns out, and that I haven't gone through that full calculation here. That's in my lecture notes, which are on the web page, but it will take a bit too long, and it's sensitive to Fourier. You really have to do Fourier transforms to do it right, so I'm not going to do it here. But you can show that this expression, which is a practical one, is equal to a statistical calculation from a random field here. And so these two are interchangeable. And so this basically tells you how smooth things are distributed, and you can use it. You can go out, you can look at the sky, and you can calculate this. This comes from our theoretical expectations, and when your model is right, it should predict the same as what you measure from the galaxies. Okay, so I'm going to continue this, I think, after the lunch break at 2 o'clock. And then I'm going to go through and actually calculate a simple way of calculating analytically this variance of the field from what we now did about the power spectrum. This is the power spectrum in that slightly different notation. We're going to put in what I calculated earlier and use that to calculate this thing. And then we will start understanding what this means. I mean, it means already something. It means how much mass there is in a particular clump. So it means that if your mass is really clumpy, so that you will typically get a lot of mass every time you hit something, and otherwise you get 0, then you get a high variance typically. And so it will measure to some extent how clumpy our distribution of matter is. But the nice thing about it is that this is observational. This is theory, and now you found a way where you can calculate the power spectrum from observations of galaxies by just counting them in boxes. And it's only a very slightly more sophisticated way that people used to calculate this distribution here. It's actually done very much the same thing. You make boxes on the sky, and you count galaxies, and then you can derive this exactly the same way I did here. Okay, it's a little bit fiddly to do it right, but in practice it's exactly what you did. Okay. Okay, so that's for later. Let's have a break.